this is an introduction that we built for you folks in order to be, for everyone to be on the same page. So the only thing that we were assuming is that you're slightly familiar with what JWST does and how more or less the detector works. If you are not completely familiar with all of that, there's many JWebinars that you can go through, and we will try to keep you, put you on the same page as often as we can as we go through this JWebinar. So the very first question that we need to answer is, what actually are time series observations? What are these TSOs that lead the name of this JWebinar number 29? And it has a pretty simple answer. So as you know, the JWST detectors read up their ramp, which means that contrary to CCDs, these near infrared and infrared detectors that we use in JWST, they divide themselves into little frames that are sometimes averaged into groups, and then you start reading on top of each other. So you read, for your favorite pixel that you pick, you have 10 electrons, and then and the next read you do 10 electrons on top of that, so you have a total of 20. On the next read, you do 10 more electrons, and you go, in this case, in this very dumb example, 30, and so on. So that's what we mean by reading up the ramp. And that actually defines what we call an integration. Then we reset the entire detector, and then we start reading again. So each of these up the ramp samples, the ramp total samples, we call it an integration. And if you have multiple integrations over what we call an exposure, so an exposure, it's a set of integrations, and you're aiming to constrain time variable phenomena, then we call that a TSO, a time series observation. So we have a visual understanding of that. Here's a little plot. So again, same thing that I explained before, our reset frame, and then you start reading up the ramp through different groups, and that defines an integration. And then you have several integrations, and a set of integrations forms what we call an exposure. And if you have something like this, and you're aiming to constrain time variable phenomena, we call that a time series observation. Now, what kind of science involves time series observations? Well, there's a wide array of science out there. Most of the TSOs that we have in JWST are transient exoplanet, but there's also a ton of other science. There's like brown dwarf variability, there's accretion variability, solar system occultations, and you name it. Basically, it's going to be going in new directions for TSOs in the next cycles. So we are eager about this mode, and in particular, it's taking like a little bit over 20% of JWST's time. So it's very important. That's why we built this JWebinar. What instruments can perform TSOs? Well, all of the 4 instruments in board JWST can actually perform TSOs. NIRCam, you know them probably, NIRCam, MIRI, NIRSpec, and NIRIS. They have the different positions, of course, in JWST, the observatory itself, and you can actually do photometry and spectroscopy with TSOs. There's certain instruments that allow you to do photometry and spectroscopy simultaneously, even, like NIRCam in some of the modes. But here in this JWebinar, we will be focusing only on spectroscopy. Some of the things you will learn, you can use as well on photometry. In terms of wavelength, NIRSpec, let's start with NIRSpec. NIRSpec has different modes that cover from 0.6 all the way to 5 microns. If you choose, for instance, to go with Prism, you can get the entire wavelength range at a low resolution. Now, typically, Prism works for quite fine-ish targets, like everything fainter than 11.4 J. It can do quite well without saturating. You want to go for brighter targets or higher resolution, then you can use the G140 and G235 and G295H or M modes that allow you to go to resolutions of like a couple thousand, and also, therefore go to brighter targets. Then we have NIRIS. NIRIS has one mode that allows you to do TSOs, which is the NIRIS sauce mode. That goes all the way from 0.6 to 3 microns. And you might be asking, well, why would I use NIRIS sauce and not the G or the Prism? And that depends on what kind of brightness you're looking at and what resolution you want. So you want to go for very, very targets and cover all the way from 0.6 to like 3 microns, probably want NIRIS sauce because it's like in one shot. But if you're interested only in like a fraction of that, then you can use the G140 or G235 for NIRSpec. Similar story with some of the NIRCam modes. In this case, I put it here like these 2 ones, F322 or F444, that cover different wavelength ranges. Also, NIRCam has the particularity that is one of the detectors that can read the fastest. So you can read like very, very bright targets with it. And finally, last but not least, MIRI. MIRI, one of the most used modes for TSOs is the LRS, low resolution spectrograph, covers all the way from 4 to 12 microns. And if you want to go to larger wavelengths than that, you can start using the MRS, which are actually integral field units. There's a couple calibration programs in case you're wondering, how stable these integral field units. There's a couple calibration programs doing MRS data, whose data is public, that you can look at. But here, the kind of TSO information that you're going to learn here, it could also, some of it be useful as well for the kind of science that you can do. Now, with respect to this last point that I just made, one thing to have in mind is that the near-infrared instruments, near-spec, near-IS, and near-cam, that go all the way to 5 microns typically, they all have the same family of detectors, which is different from the kind of detectors that MIRI has. The implication of this is that whatever you learn in the near-infrared detectors, sometimes it will not sample one-to-one to the infrared MIRI detectors. So you have to be a little bit careful with that. So today we're going to be talking a lot about near-spec, and a lot of the information that you'll gain today, you can transpose it to near-cam or near-IS and so on. But making use of that information from MIRI, you have to be a little bit more careful because there's different detector effects. Like two different beasts, these near-infrared instruments and the infrared instruments that are on board with MIRI. All right, so there's a lot of TSO datasets that you can explore out there. And we're going to be focusing today on one particular dataset that is part of this very beautiful project, which was the Chance in an Exoplanet Early Release Science project. These were a set of programs that were given through the director's discretionary time to the community so they can get the first science out of JWST. And in particular, this team did a lot for transit and exoplanet science. So these are TSOs for all instruments, actually, that contain scientifically interesting spectral signatures. Probably the one that you've seen around in the press a lot is this family portrait for different instruments. And these beautiful features of like water, CO2, sulfur dioxide, and even sodium and potassium over there within NIRS and NIRSpec. And this is the atmospheric composition in particular as observed from JWST for WASP-39b. And that's just one part of what the ERS did, which was, again, observing the exoplanet WASP-39b, through primary transit. So when the planet passes in front, and then some starlight gets filtered through the atmosphere, and that same technique was used to observe with NIRCam, NIRSOS, NIRSpec Prism, and NIRSpec G395H. Again, this is just one of the amazing things the ARS team did. They also got a secondary eclipse with NIRSOS for WASP-18b, which is when the planet passes behind. And they also measured a full phase curve of an exoplanet, WASP-43b, with MIRI LRS. Today, we will be focusing on the observations of WASP-39b for NIRSpec G395H. This is what this JWebbinar will be focused on. But as I told you before, a lot of the information that you will gain now, you could use it to analyze the other datasets from this team and other datasets out there. General flow of the TSO pipeline and data reduction. So data reduction, as understood by the JWST calibration pipeline, has stages, we call them. There's 3 of them. And each stage is like a big chunk of a lot of little steps. So little steps that get you from one level of the data to a next level of the data. To give you an example, stage 1, for instance, takes care of everything that is happening with the detector. And it's composed of many steps that we're going to say in a minute. After stage 1, it comes stage 2, and the idea of stage 2 is that it extracts an actual spectrum out of your data, and then comes stage 3, in which you actually get like a white light curve, so you can plot your little transits out of there. Cool thing that you'll see today is that in this JWebbinar, we expect to give you a tour through stage 1 calibration, so everything that is detector,